Hello mathematicians. The last thing that we look at in this chapter is inverse relations and functions. Now we are just going to touch on this, which is good and bad. Good in that we're not going into a great amount of detail. Bad in that that means that you have to take a lot of things on trust. This is genuinely extension 1 material. You do a chapter or several chapters later on inverse functions. But this is just a taster. So an inverse function, or probably more correctly for the moment if we call it an inverse relation, is formed when you reverse each ordered pair in a relation. In other words, the x and the y values in a relation. So you effectively undo it. So if we had the cube root of a cube, for example, or the cube of a cube root, we're undoing those things. To find equations and conditions of the inverse relation, the technique is relatively straightforward. We replace x's and y's in each side and solve the equation for the other variable. So if we had y equals x cubed, for example, when we switch the x and the y, we get this, and then we solve it to make y the subject. So the inverse functions or relations are y equals x cubed and y equals the cube root of x. And as we said before, if we have a particular value of x and we operate the relation and the inverse relation one after the other, we get back to where we started. So if I cube a cube root or take the cube root of a cube, I'm back where I started. So let's have a look at some examples. Hopefully it will make this process just a little bit more obvious than that blurb up there. So if I have y equals 3x minus 2 as the original function, then I swap the variables, so I get this. Now I make y the subject again, so y equals, that will be x plus 2 all divided by 3, so it will be x on 3 plus 2 on 3. Then this is the inverse function. Now, I'm going to have a look at the graphs here because that brings out an important point. So if we had the graph of y equals 3x minus 2, we know that that cuts at minus 2. It has a gradient of 3, so it goes up there. It cuts through the x-axis when y equals 0, so that will be at 2/3. Now, if I graph this thing here, and I'll do it in a different colour, this graph cuts at plus 2/3. My drawing's going to let me down here. Cuts at plus 2/3. It's got a gradient of 1/3. So that means it will cut through the x-axis when y equals 0. So that will be at 2. So out here at plus 2. So the line would look like this. Now, if this was all drawn nicely, then if I drew the line y equals x in here, we would see that these two graphs are reflections of each other in the line y equals x. Now we're not required to do that here for all of these, we just have to end up with the inverse function. It might also be worth thinking about if I put a value of x into here and worked out that value of y, and then I put that down into here, where would I go? So for this one, this is our function, swap the x and the y around, make y the subject, so if I double everything, 2x equals 6 minus y, so y equals 6 minus 2x. Again, for what it's worth, if I drew these two graphs on the same set of axes, they would be reflections of each other in the line y equals x. And once again, you might want to think about what would happen if we substituted a value of x into the function. Say I put x equals 1. Then that would give me a y value of 2.5. And then if I looked at my inverse function down here, if I put that value of 2.5 into here, 6 minus 2 times 2.5 is 6 minus 5, which returns me a value of 1. So it's like I do this thing here to change my 1 into a 2.5, and then I do this thing down here to change my 2.5 back into the 1. So that's why these are inverse functions. One cancels out the other. Okay, I won't do E, you can do that for yourself. Now, as a consequence of this changing of the x and the y, it means that the domain and the range are actually exchanged. So the domain of the inverse function is the range of the original function or original relation, and likewise the range of the inverse function is the domain of the original relation. As a result, we can, if we know the shape of the graph of the original function, so in this case y equals x cubed, we can reflect that in the line y equals x, so that's effectively putting y equal to x, and the curve that we get, this one here, is the inverse function. So for y equals x cubed, then y equals a cube root of x is the inverse function. And again, it fits with the fact that if we cube a number and then take the inverse cube of it, we will be back to the number. Let's have a look at some of these examples. I'll be selective given my limited drawing ability. So if we want the inverse relation for these relations below by reflecting in that line, the first one I think I can cope with. That will go something like that. This one here, when I reflect in the line, actually I was probably a bit overconfident there, but I think it will go maybe something like that. That's terrible. This one here, it will go like that. And this one here, I would really struggle with, but I think it will go something like that and something like that. Rest assured you're not going to, as I said in class, get too many questions that require you to draw this, because they'd be terrible to mark. We're starting to dip pretty deeply into this at the moment, probably more deeply than we need to at this level, but let's go on. So while every relation has an inverse relation, not every function has an inverse function. And you might not be surprised to realize that we can test for the existence of an inverse function by a horizontal line test. And we can also test algebraically, but the horizontal line test is the quickest. So if we look at this function that we had up above, y equals x cubed, it is definitely a function. It passes the vertical line test. And if we look at the inverse function down here, it passes the horizontal line test. So a horizontal line doesn't cut in any more than 1 point. Whereas over here, for y equals x squared, that is a function because it passes the vertical line test. This thing here is not a function because it fails vertical line test. Failure on the horizontal line test means that we do the horizontal line on the original function. So on this original function, if I draw a horizontal line and it cuts more than once, then my inverse function is going to have a vertical line which cuts more than once. Now this point here about the inverse function can be written as f to the minus 1 of x, and if we take the inverse function of a function or the function of an inverse function, if those functions exist, they will return us to our original value of x. And that's the algebraic test of whether the function has an inverse function. It's clearly more fiddly. Well, if we are provided with graphs, the algebraic test is clearly more fiddly. If we haven't got the graphs, it may be 6 of one, half a dozen of the other. So let's have a look at these examples. So our first one, if this is the original function, f of x, and we do know that that's a function because x cubed plus 2 does that, so it will pass the vertical line test. And it will also pass the horizontal line test, so it has an inverse function. The inverse function we're going to find by first of all swapping x and y, so that will give us, remember that f of x is just y, so if we say y equals x cubed plus 2, therefore swap them over, x equals y cubed plus 2, then x minus 2, when we swap that over, take the cube root, that will be y. So this is our inverse function. Now I'm not going to try to draw that. Suffice it to say that it's a reflection in the line y equals x. And what I could do to check algebraically is to take a value of x, plug it into this, put the output of that into this, and see whether I get back to the original value. Over here, f of x equals x squared minus 9. So this is our original function. We know that that's a parabola cutting down here at minus 9. It's a function, but it's going to fail the horizontal line test, which means it doesn't have an inverse function over the full domain. So we would have to restrict the domain if we were going to get an inverse function. And in fact we know that's the case, because if we have y equals x squared minus 9 and we swap the variables to get that, so that we get y squared equals y squared equals x minus 9, we know that y squared equals x minus 9 is a parabola lying on its side, so it will fail the vertical line test. But if we break it up into y equals square root of x minus 9 and y equals minus square root of x minus 9, both of these, the upper and the lower branches of our parabola, are indeed functions. So the inverse relation is this one. If we wanted to have inverse functions, we would have to break it into two separate areas. So we'd have to essentially interchange what was the domain of this, all real x, and the range, y greater than or equal to 0, down to, for this thing, the domain becomes x greater than or equal to 0, and we have a restriction as a result on y. That point above is demonstrated here on this graph. Y equals x squared is a function, but it doesn't have an inverse function. But if we restrict the domain of y equals x squared, then we will have an inverse function over that same domain. Okay, so have a go at these. Again, remembering that we are really on the pointy end of the topic at the moment. The difficult ideas, precursors to extension 1 material, or indeed extension 1 material. So don't feel discouraged if they're taking some real concentration to get some of these out. Remember, answer the question as written.